So, hi. As you've heard before, my name is Carine Belle. I'm a software engineer in Oracle Ravello's virtualization group, and I'm very excited to be here because I love both virtualization and security, and I'm really happy to talk about their combination. And you can find me on Twitter. Okay, so today we're going to talk about two things. This talk is going to have two parts. In the first part, we're going to talk about an intro to virtualization. What is it, like how does it work, and so on. And in the second part, we're going to talk a bit about how it relates to security. So let's roll. So as some of you probably know, virtualization is one of the most abused words in tech. We virtualize everything. We virtualize realities, and we virtualize networks, and we virtualize practically everything. But today, we're going to talk mostly about hardware virtualization. So let's start with defining what is virtualization. It's practically the idea of creating something new over an abstraction layer. So in this case, we're creating an abstraction of the operating system to run another operating system on top of it. So this is what we're going to talk about today. But even in tech, in this type of virtualization, we also have a lot of types of virtualization. So as you might see, we also have application virtualization, which is kind of like an example would be the JVM, the Java Virtual Machine that compiles Java code. And another example would be network virtualization. So if we have a running network with IP addresses and everything, and we want to create another layer of an IP network on top of it, we'll create a VPN, which is a virtual private network. But we're going to talk about hardware virtualization, as we said before, which means virtualizing hardware, such as the CPU, the memory, the storage, even your keyboards, your screen, whatever. Okay, so as we said before, this is what hardware virtualization means. So why would you do that? Why would you do such thing? So the most common use to such virtualization would be to utilize resources. So let's say we have 3 operating systems. I could run them on 3 different hardware, but that would be inefficient, right? Because as you can see, it wastes a lot of hardware resources. So what I can do instead, is run them all on one hardware and make them think that they control all the resources. Now, in the case that I need more resources than I already have, I can sometimes ask for more resources just for that instance of time. So this is basically how cloud works, right? Because we ask for resources, and then if we need more, we ask for a bit more. The other common reason is to create flexibility. Let's say I work daily on a Linux machine, but for the next week I want to work on a Windows machine. So I could reinstall an operating system on top of my hardware, but that would be a pain in the ass, right? Like, I wouldn't want to do that. So what I can do is run on Linux most of the time, and then when I want to run on Windows, I would just click and run my Windows machine. And the last and most relevant use in this audience is research. As Sebastian showed before, sometimes I want to run malicious code or try out things that I wouldn't want to run on my own operating system, in my own environment. And I would do that in a separated, isolated environment. So these are 3 of the most common uses to virtualization. Of course, there are more, but these are the most common. So, taking from what we just talked about, we have 3 main requirements for this technology. So the first one would be provide an equivalent environment. So if I run malicious Windows code, I want the virtual machine to behave exactly as if it's a native Windows on my own hardware, right? Because otherwise it would be weird. And even if we're going to the utilization use case, we want it to run exactly the same because it's like my production environment or the app I run for my users and so on. So this is the first requirement. The second one is that I need my environments to be isolated. It means that if I run two separate virtual machines, I don't want one machine to affect the second one, not its memory, not its CPU, not whatever. It would be totally wrong if one Windows machine would run a malware and that could access another virtual machine with Windows. And the last one is at least similar performance. Why would I say at least and not the same? That would be because it's a very difficult task. And we still work on it to this very day. Okay, so these are our three main requirements. And like many other good things, they have stuck with us since the 70s. Awesome. So let's start with our need-to-knows. There are several things we need to know before diving in. And the first one would be the host guest machine wording, which means I would call any machine and any operating system that actually controls my resources the host machine, and the one that's running on top of it and being virtualized, a guest machine. That's easy, right? But if I run a guest on top of a guest, that becomes complicated, right? So at this point, I would call them levels, but that's aside. Another thing important to know is that every operating system, and mainly our relevant ones, have four privilege levels, especially x86, because it's relevant to this talk, but any other architecture as well. Okay, but usually we use only ring 0 and ring 3. So we'd call ring 0 kernel mode, and we'd call ring 3 user mode. And every request that doesn't need high privilege would usually run in user mode, and every request that needs more privileges to access a more interesting part in memory and so on would be run in a kernel mode. Okay. More need-to-knows. So another need-to-know is what is a hypervisor. So a hypervisor is basically the piece of code that runs the virtual machine. We separate them to two different types. We call them type 1 would be a one that is also an operating system. It would run by itself and then would run operating systems on top of it. Then it manages to utilize your resources way better because all it cares about is running virtual machines. We also call this hypervisor bare metal. Type 2 would be one that runs like an application. And then I could run my Windows machine, do whatever I want, and then as a part of my research, run a virtual machine on top of it. That would be type 2. Okay. And the last important thing that we need to know is something called a binary translation. So every app has its calls to the CPU. And as we said before, some of them are running in user mode and some of them are running in kernel mode. So when a virtual machine runs, it also needs to run all sorts of requests from the CPU, all sorts of calls to the CPU, and some of them are in user mode and some of them are in kernel mode. The thing is that someone needs to translate all the interesting requests from the virtual machine to the hosting machine, to the hosting operating system. So a binary translation is basically taking all this privileged requests and translating them into something that is decent for the virtual machine to run, which would be making sure that it's using a decent memory, not too privileged memory, or doing correct operations. This is a process that takes a lot of time. Think about every time that an application requires to do something in kernel mode, and then it takes a bit of time, but when a virtual machine wants to do that, it goes through the whole process of the hypervisor catching this request and then translating this to something that is okay for a virtual machine, and then passing it on, like an app, to the CPU. This process takes time. So something that we do as a part of it is caching translation, which means, let's say I translated request A and then moved on with my life, and then after a while, request A comes again. So instead of retranslating it, I would take it from the cache. That's a way of saving time, which is something that is really important when talking about virtual machines, because running virtual machines take time and they move slow. This is one of the reasons they're so slow. Okay, so we've discussed a lot of need-to-knows, and now we can talk about all these types of hardware virtualization. So we're going to talk about what is full virtualization, paravirtualization, and hardware-assisted virtualization. So full virtualization in this scope is easy because all it does is binary translation. It just translates everything that it catches. Everything the hypervisor catches would be translated by the hypervisor. It's basically what old versions of VMware used to do. Okay. The second type is paravirtualization. This is more interesting. The concept behind it is, okay, let's say people looked at virtualization and said, okay, this is slow, and this is annoying. Let's say I'm okay with my machine knowing that it's being virtualized. Let's say I'm totally fine with it. When researching malware, we don't want to do that. But in other use cases, that would be fine. So what they said is, okay, let's create a system that, let's modify the operating system in a way that when it sends requests that need real interesting privileges, it would stop, say, okay, I know this is going to be difficult, translate it itself, and then send it to the hypervisor. This is paravirtualization. The problem with this is that most operating systems don't want to modify themselves in this sense. It works basically more with open source operating systems, such as Linux. And this is how we got to have Zen operating system, which is a paravirtualized machine. It knows that it's being virtualized, and that's why it's running faster. The third type of virtualization is hardware-assisted virtualization. This came out in 2006 when manufacturers like Intel and AMD realized that virtualization is a big thing, which is good because it's here from the 70s. And they said, okay, what we need to do is create something that supports this concept, this technological concept. And what they did is creating more instructions that recognize the fact that these requests to the CPU came from a virtual machine and say, okay, I'm good with this running in this part of the CPU. This is a virtual machine's request, and it runs differently. Okay, so they created a VTX, Intel, and AMD, which support hardware-assisted virtualization. When it's not supported, when it's not a supported request, it would still be binary translation. Those of you who know more virtualization environments would know that KVM is an example, is an open source example of a virtualization that relies on VTX or AMD being existent on this hardware. Okay, this is not good. Awesome. Okay, so we've talked a lot about what is virtualization. We talked mostly about CPU virtualization and how it works. And I think it's important because we use virtualization a lot when we do security research And most of the time, we don't know how it works, and we don't know what's the meaning of running it on top of a virtual machine. We just use it. We use virtual machines, we use Docker, we use virtualization all the time. And most of the security people I've talked to didn't know what it means. Okay, so let's talk about how virtualization and security are combined. So the first thing I want to tell you is don't always assume that because you're working with virtual machines, you're protected. You still need to know your environment. A hypervisor is just another tech that you can hack. So as if you would never assume that just because you're using a firewall, you're protected. So this is the same way you should behave to virtual machines. The second part is that I wanted to note or to mention a term that is very commonly used, which is VM escaping, which is kind of the holy grail of people who do security researches in the virtualization world. What it means is the ability to get from a virtual machine to a host machine and run malicious code on the host machine. This is a very rare ability, and it's worth a fortune, and for a good reason. It's not common, it's not easy to find, and it's very dangerous. Just imagine that someone could do that on virtualization that's running on the cloud. How many people would be sad at that day? The third thing I want to refer to is a very cool vulnerability found in 2009 by Kostya Koczynski, and I really hope I say his name right. It was presented at Black Hat in 2009, and I think it's one of the simplest and most interesting ones. So this vulnerability is called Cloudburst, and the vulnerability was found in one of the device drivers that VMware used to run their products. So the reason he did that is firstly because I/O devices transfer a lot of data. So he thought it would be an interesting place to search. Another good reasons would be because they're common in all VMware's product, as they're run on all types of, like both type 1 and type 2 hypervisors, and everyone needs them. And the last thing is they share a lot of host and guest memory, which is also cool. So the first thing he did is look at all these device drivers, and what he said was, okay, those are the device drivers that I know to be used a lot. And the first one he said, okay, let's look at the video adapter. So this is a device driver that transfers a lot of data, and when I say video adapter, I mainly refer to the use of it as presenting things on the screen. This is the main thing it does. Okay, so what he did is to look at where the device driver shares data between the host and the guest. And these are the main two things he found. It's first the SVGA FIFO, first in, first out, and the second thing is the frame buffer, which is another place they would share memory. The next thing he did is look at all the functions in this device driver. He crossed out all the deprecated ones and then marked in green the most common used. And then he looked at them for a while, and then he said, okay, what I'm gonna do is use this one that's called SVGA CMD rectangle copy. As you might imagine, what it does is copy rectangles from one place to another, which means copy a pixel on the screen from source to dest. And what this function takes is a pointer and size that refers to a place on the screen, and a destination, which is also a pointer and size. And this is cool because what he thought to himself was, what could happen if I could point to a not legitimate place in memory? And what he found out, that boundary text on the source location can be bypassed. So what he managed to do is pretty easily just point to a different location in memory and say, okay, I want to copy from this source that is not really a pixel in the screen to the destination, which is in the virtual machine's memory. This is amazing, because what it does is taking memory from outside the frame buffer, reading memory of the host from outside the frame buffer that was assigned for that virtual machine, and copying it into the frame buffer, which the virtual machine is allowed to read. So what is amazing in this vulnerability that it allowed him to read host memory from the guest machine, which is mind-blowing. Like, think about how clouds work right now. If someone that is running a virtual machine on top of the cloud could read data off the cloud memory. So the natural thing that he did next was say, okay, so if I could read from a privileged location, could I write to it? And apparently he could. So it wasn't as privileged as before, and it had limitations, but he could also write outside the frame buffer. This is not like executing code. This is more like writing to and from the stack. But it's still an amazing ability, which should not be in VMware's product. He reported this vulnerability and they patched it, but it's still something that is pretty amazing. So concluding this talk, I want to say 3 main things. The first one is using virtualization is inevitable. We use it all the time. We don't need to escape it. We run virtual machines when using the cloud, as I said 1,000 times. We use virtualization when we research malware and when we do all other things using the 1,000 types of virtualization. But it's better to be smart than sorry. It means that it's better to know what is your tech made of instead of just using it and hoping for the best. As security people, we need to know what our environments are made of, and if we research them, we need to know they're even better, hopefully. The last one is my own opinion. I have a lot of faith in open source. Open source is a place where you can learn more about the tech you use, and you can count on the fact that a lot of people have done research on it, and if something is found, a lot of people would have a good reason to patch it. So I have a lot of faith in open source, and this is a good way, in my opinion, to be protected. So this is all I wanted to say today. Any questions? Okay, again.
We have another, yes, we have another microphone, yay.
The 3 or maybe it was 4 rings model, where it's used actually, because like what are the 2 middle ones?
The privilege levels?
Yeah, the ring 1 and ring 2.
I've not seen any use of them, but they might be used somewhere, but they're not commonly used.
Okay.
Any more questions? Okay, thank you very much.